Okay, what we need to do now is we need to create this rotating field, this rotating magnetic field, so that we can cause this rotor to turn. All right, so we need to bring in three-phase electricity, three phases of electricity into the stator, and cause this rotating magnetic field to occur. Let's look at how we might be able to do that. All right, let's see how this works for us. This is a place I like to go to a lot. This Wisconsin Online. This particular one that we're looking at is three-phase motor stator field. And what I want you to look at here is that there are three phases of electricity, okay? And so this would be phase one, and here's another phase here, and here's another phase here. And these three phases of AC electricity are brought into these pole pairs, A1 and A2, B1 and B2, C1 and C2, okay? Now, as I look at this, the stator of a three-phase AC motor, it has these coils wound on pole cores are equally spaced within the motor frame, right? So, you know, if you could think about this particular one, 360 degrees all the way around, there are 6 of these poles. So 60, I mean, from here to here, 60, 120, right? 180, 240, 300, and then back to 360, right, all the way around. And this is showing the three phases of electricity. These are the stator coils, and so this is inside the motor frame. Okay, now, because current is going to flow through these wires here, it's going to create an electromagnet, and each one is going to have a magnetic field. So what he's showing these three stator coils creating flux lines that form a resultant magnetic field that continually rotates. Okay, let's look at the next one. The coils are physically placed 60 degrees apart. The coils in each pair are wound around cores that are located opposite each other. Okay, so this is a pole pair, pole pair, pole pair. Okay, so we're going to label this phase A, and this is phase B, and this is phase C, just like we might expect that to be, right? All right, now, if we looked at each one of these, here are three phases of electricity that we're going to bring in. All right, so here's phase A, and here is phase B, and here is phase C. And what we would see if we could, and we'll show you here in a little bit, but each one of these voltages are 120 degrees apart, okay? So each one of them, if you looked at them, you would see 120 degrees of separation. So we'll click on each time period of the three-phase voltage and apply it to the stator cores and observe the resultant field, okay? So watch what happens here. I'm going to click on T1. So at T1, this is showing phase A, and we see that this magnetic flux is created here. At T2, we're seeing phase C, and we're seeing the magnetic field here, okay? And we're just progressing along with this, right? We're just moving right along. T3 here, right? T4, back to here. T5 here, T6 here. So what we saw was this magnetic field, it circled, right? It went all the way around the circumference internal of the stator. Now, to see how this rotating stator field is formed, examine this diagram. It shows the instantaneous voltage and polarities at each phase of the AC supply at different intervals. It also shows the direction of the corresponding electron flow through the coils. Not sure that that's particularly important, but what we see, you know, here at this point, and something you'll see that's very, it's kind of neat about this too, is, you know, when phase B is at 120, you see that phase C and A are both at minus 120, so they basically cancel each other out, right? And so, you know, that's something to observe. But at every point, if you picked it up at every point, you'd see that they're the same. Not that that's the most important thing about this right now, but what we can see is this rotating magnetic field across here as the three phases of electricity go through. Okay, so the AC voltage for each phase is connected to corresponding terminals with this symbol. The terminals at the opposite stator coil are connected to zero voltage ground. And you can see these representations of that. Okay, so, you know, phase B is at its peak at the positive of its alternation. So that's right here. Okay, the current through the B coils is 20 amps. Phases A and C are negative at half the voltage phase B, resulting in 10 amps of current through the A and C stator coils. Okay, so this is shown here, right? And this progresses through here at this time point 0. So that current is 20 amps, and the current in C and A is at 10 amps each, so they come out to be the same. And what we would see is anywhere in this diagram, the current will be the same based on the three phases of electricity that we look at. Okay, so at time period 0, the B coils with the strongest magnetic field are aided by the fields created by adjacent A and C fields to form the resultant magnetic field shown with the green arrow. Okay, so overall there is this dominant magnetic field with a particular direction comprised of the contribution from phase B, C, and A, and this is how we develop that rotating magnetic field there. Okay, now I think he's going to walk through all of these, you know, and doing it again with time period 1 and so forth and so on. Now, I don't want to do that. You know, you kind of get the idea about what's going on with this at that point. And so, you know, it's just redundant to go through this whole thing. All right, so that gives us a little overview of this three-phase electricity brought into the stator. I'm going to stop that there. We'll make this part 1.